Hello, so today we're going to be talking about the ideal gas law. I'm going to tell you up front that you do not need to memorize these three gas laws that are on the slide, but you do need to know the concept behind each of these. As we'll see in a few minutes, you can actually derive each of these three laws from the ideal gas law. Okay, so to start off with, it's been found experimentally, years and years ago, centuries ago, that there's different relationships between the pressure, temperature, and volume in an ideal gas. And these gas laws have names based off of the people who discovered them. Again, you don't need to memorize any of these laws other than to know that they exist and to have a basic understanding of how these relationships work. So the first one I want to talk about today is called Boyle's law. And what Boyle's law says is that the volume of a given gas, okay, so this focuses on volume of a gas held at constant temperature. Okay, so the temperature is fixed, varies inversely with the applied pressure when the temperature and mass are constant. Okay, now this word varies inversely basically means that there is an inverse relationship between volume and pressure of an ideal gas when everything else is held constant. Okay, now the way I'm going to write that is I'm going to say that the pressure of an ideal gas is proportional to, okay, I use this proportional symbol, 1 over V. Okay, now this word inversely is telling you what type of relationship exists between these two variables. Now, there's a difference between a linear relationship and an inverse relationship. Okay, an inverse relationship, if you were to, let's say, make a graph of pressure as a function of volume. Okay, let's say you take a gas and you increase the volume and you see how the pressure changes, then that inverse relationship would look something like this, and there would be like an asymptote here. Okay, so there's an inverse relationship for an ideal gas. There's an inverse relationship between volume and pressure, assuming everything else remains constant. Okay, then you have Charles' law that says the volume of a given amount of gas held at constant pressure. Okay, so now the pressure is kept constant. The volume is directly proportional to the Kelvin temperature. Now, it is important that you understand that when we talk about gas laws, the temperature must be measured in Kelvin. Okay, that's very important. When we did specific heat capacity problems, change in temperature can be either in Celsius or Kelvin, but any equation that has temperature in it has to be measured in Kelvin. Okay, and so this Charles' law is saying that the volume of a given amount of gas held at constant pressure is directly proportional to the Kelvin temperature. Now, there's a difference between an inverse relationship, which we saw before, and a proportional relationship. A proportional relationship, I guess I should tell you, a proportional relationship is a linear relationship, and it's a special type of linear relationship. And so the way I'm going to draw this out is basically, let's say, we measure the volume of a gas and see how it changes with temperature, assuming that the pressure and the amount stay constant. A proportional relationship would look something like this. Okay, a proportional relationship is a linear relationship that goes through the origin. Okay, so that's way different than an inverse relationship that looks something like this. And then you have Gay-Lussac's law, which says that the pressure of a given amount of gas held at constant volume is directly proportional, there's that word again, to the Kelvin temperature. Okay, and so that's just saying if you were to make a graph of pressure as a function of temperature for an ideal gas, assuming the amount and the volume was kept constant, remember a directly proportional relationship looks like this. Like this. It's linear going through the origin. Ignore that little bit right there, actually. Maybe I should erase that so you don't get confused. Let me see if I can do a better job drawing this. So something like this, a linear relationship going through the origin. Now, the reason I told you that you don't need to know each of these three laws is because we're going to talk about on the next slide about what's called the ideal gas law. And the ideal gas law is basically going to combine all of these concepts into one big equation that we can use. And then we can always work backwards from that to derive any of these laws that we just talked about. So pause it here if you need to write any of this down in your notes. The last thing we're going to talk about is, can these laws be explained in terms of the microscopic behavior of gas particles? Okay, and we've talked about the microscopic understanding of matter in the past, and the microscopic understanding of temperature and pressure and things like that. And so let's just go through this really quick. Boyle's law says that the volume of a gas held at constant temperature varies inversely with the applied pressure when the temperature and mass are constant. So in other words, bigger volume means less pressure. Now, based off of the microscopic viewpoints we've talked about before, we know that the pressure of a gas has to do with the frequency of collisions that the gas particle is making, right? If you increase the volume of the gas, that means those collisions happen less often because they have more room to move around it, okay? And so the collisions don't happen as often. So that makes sense. Boyle's law makes sense in terms of what we understand about the microscopic behavior of gas particles. If you look at Charles' law, it says that the volume of a gas at constant pressure is directly proportional to the temperature. Okay, so in other words, if the pressure is constant, if this frequency of collisions remains constant, if we increase the temperature of the gas, right, that means each gas particle is moving faster. So remember, temperature measures the average kinetic energy of the gas particles. If the gas particles are moving faster, but the pressure is remaining the same, the only way for that to happen is if the volume increases, right? Because if they're moving faster, they're going to collide more often unless they have more space to move around it. Okay, so that also makes sense in terms of microscopic behaviors that we've talked about. By the way, an example of that would be like taking a balloon filled with air. If you heat up the balloon is going to expand. Okay, because again, if you want it to be held at constant pressure, that means you need the frequency of collisions to remain constant. If the particles are moving faster, as you increase the temperature, you also have to increase the volume in order for the frequency of collisions to remain the same. And then Guy-Lussac's law is probably the most obvious one on here. Of course, if you keep the volume and the amount constant, if you increase the temperature, that means on average the gas particles move faster, and if they move faster and the volume isn't changing and the amount's not changing, then they're going to collide more often. Okay, so all of these can be understood in terms of the microscopic viewpoint that we've talked about before. Okay, and so pause there if you need to rewind and review everything I just said, because on the next slide we're going to talk about the ideal gas law. Okay, so I'm going to erase this. Okay, this is just a graphical representation of the three laws we just talked about. They look a little bit different because they're graphed slightly different than what I talked about before. Also, if you look at this graph up here, they've actually graphed this kind of incorrectly. I don't know why it says meter to the -1 power. That's not the correct unit for volume. So two of these are correct. I don't know what's going on with this one right here. Okay, so here is the ideal gas law, and I state this without proof. It says this is what's called an equation of state. An equation of state and state variables basically just have to do with what is the current state or status of the situation. Okay, and so here's what the ideal gas law says. It says PV equals nRT, and I'm sure you've seen this before. P, of course, is pressure, V is volume, N represents the number of moles of the ideal gas, R is a constant. The units that we're going to be using for R make it so that the value of this constant, this is called the gas constant, is about 8.31. And then T is the temperature measured in Kelvin. And I know you've seen this before in chemistry, but this is called the ideal gas law. Okay, and then on the rest of the slide, it tells you what all of the variables mean and what units they should be measured in. Okay, so make sure you put that down and add that to your notes. We're not going to do any crazy problems with the ideal gas law. You're not going to have to worry about balancing equations or stoichiometry or anything like that. But you do need to be able to solve basic problems with the ideal gas law. And I should say this, it is in the notes, but I should say, even though this might be obvious, I'll still say it. This is the equation for an ideal gas. This is the ideal gas law. Ideal gas law. So that means that this equation only applies if you have a situation with an ideal gas. In other words, if you meet the criteria to assume that your gas behaves like an ideal gas. Now, what if it's a real gas? What if it's not an ideal gas? Well, then the equation would not look like this. It would be more complicated than this. And that's something that you would probably see in like college level chemistry, either first semester or second semester. It's not something that you would have to worry about for this class, and that's not really a high school thing. But you should know that if this was a real gas and not an ideal gas law, this equation would not apply, and the equation would look kind of sort of similar, but it would be more complicated than this. So this is only for ideal gas. Okay, so make sure you know what the ideal gas constant is, and make sure you understand what the units should be. Pressure should be measured in Pascal. We talked about that before. Volume should be measured in cubic meter. N is the number of moles. And then T should be the temperature measured in Kelvin. I said that before. Okay, so I'm going to erase what's on here. You can pause it here if you just kind of want to write down the chart that tells you what everything in the equation represents and what the units are, and the gas constant, all that. And now we're just going to do some basic equations and calculations with the ideal gas law. Okay. So I said this before, this equation only applies if the gas can be treated as an ideal gas. And by using the ideal gas law and assuming some of the variables are constant, you can derive the previous three gas laws. And I think we'll see that in one or two examples. We can actually go backwards from the ideal gas law and kind of figure out those relationships that we talked about before, like Boyle's law, Charles' law, stuff like that. Okay, so first we're just going to do a very, very basic example. And this is example 1, and it says how many moles of an ideal gas would it take to occupy 0.0025 cubic meters at a pressure of 1.5. This big M is mega. Okay, so that's megapascals, and a temperature of 250 degrees Celsius. And then there's an explanation question that we'll get to here in just a second. Okay, so first of all, I'm just going to move this up so I have some space to work with. Okay, so I'm going to do this on another screen, but first I'm going to identify my variables. Okay, so I'm asked to find the number of moles, so that is a lowercase n, of an ideal gas. If it's an ideal gas, that means I can use the ideal gas law, which is good, PV equals nRT. Would it take to occupy, so based off of the unit, this is the volume. Okay, so there's my volume. The pressure, make sure that you convert that to pascals. Remember, mega is 10 to the 6, so that would be 1.5 times 10 to the 6 pascals. And the temperature is in Celsius. And remember, temperature must be measured in Kelvin. Change in temperature can be in either one, but temperature must be in Kelvin. So temperature in Kelvin is going to be 250 plus 273. Okay, and so that would be 523 Kelvin is the temperature. Okay, and so write that down if you need to, and we're going to solve it on the next slide. Actually, I think I can probably fit it on this slide. This is a pretty basic problem. From the ideal gas law, if we're looking for N, we have N equals PV over RT, which is very basic rearranging right there. And then all we have to do is plug in the values. Now, the only way you can mess up these problems is if you get the units incorrect. Okay, so please pay very close attention to the units. Make sure everything is converted correctly. In this case, we don't have to convert the volume, which is good. We have R, the gas constant is 8.31, and then the temperature in Kelvin is 523. So I'm going to type that into my calculator, and that tells me the number of moles that I have of the ideal gas. By the way, as I type this into my calculator, one of the cool things about ideal gases is that if we can treat a gas as an ideal gas, the identity of the gas does not matter. Okay, and so this this calculation could work for helium, it could work for oxygen, nitrogen, whatever gas we want, as long as we can assume and treat it that as though it's an ideal gas, which may or may not be a good assumption, but does not depend on the identity of the ideal gas, which I always thought is kind of interesting. Okay, and so this is the answer to the first question. Okay, so very easy calculation using the ideal gas law. Remember, it's that lowercase n that represents the number of moles of the ideal gas. So pause it here if you need to, and then we're going to talk about the second question on here. Okay, so I'm going to erase what's on the screen. Okay, and let's see if we can't answer this question in words. It says, explain why the actual value for the number of moles might differ from the value you calculated in the previous problem. And I've alluded to this before. The ideal gas law works as long as you can assume that the gas is an ideal gas. Okay, and so if I'm doing this explanation question, remember when you want to explain or when you want to answer an explain question, you need to write in complete coherent sentences and make sure that you answer the question being asked. Okay, so I'm going to start with saying the actual value for the number of moles might differ from this value because, okay, so that's just how I'm going to start off. That's part of answering a question coherently, is kind of restating the question. Because this equation only applies if the gas is actually an ideal gas. Now, you might think that is a good enough answer, but that does not fully answer the question. I need to go one step further and say, does that answer the question? Why might the actual value for the number of moles differ from the value we calculated? Well, okay, so this equation only applies if the gas is actually an ideal gas. So what? Well, this gas might not be treated, or let me think how I want to word this. This gas may or may not behave as an ideal gas, which means that the actual value might differ. Let me autofit this. Value for the number of moles might be different from this value. Okay, or something like that. Okay, so if this was a test question, this is probably like a 2-point question. Okay, please make sure that you answer the question being asked in complete coherent sentences. Okay, so I'm going to go to the next slide. I'm going to erase this, so pause it here if you need to. Okay. A couple more examples. What is the pressure of 23 mole of an ideal gas, of a gas behaving ideally in a 0.25 cubic meter container at 310 Kelvin? This is another super basic calculation question. I can just do this very quickly. PV equals nRT. I'm looking for pressure. I have N, the number of moles. I have the volume, and I have the temperature. Okay, and this is actually easier than the last one because just looking at the problem, we don't need to do any unit conversions. So I have 23, I have 8.31, I have the temperature in Kelvin, which is already given to me, and then I have the volume in cubic meters, which is already given to me. And so all I have to do is type that into my calculator, and I will be done. Okay, so some of these problems are very, very basic. Okay, so this is 237,001 pascals. Or if you wanted to save yourself some time, you could write 237 kilopascals. Either way is fine. I guess that this would maybe be the best way to answer the question since that's in the correct units. So pause there if you need to look over that. Again, just a very basic calculation. Okay, so I'm going to erase this. Example 2, it says, show that the combined gas law can be derived from the ideal gas law if you assume that the number of gas particles remains constant. The combined gas law says, and then they give you an equation. So this is a gas law that we didn't talk about. This is called the combined gas law. And basically this problem wants us to derive this, or come up with this equation, starting from the ideal gas law. Okay, and so I'm going to show you how this works. Okay, so we have PV equals, let me draw that better. So we have the ideal gas law, which says PV equals nRT, and somehow we want to end up with this weird-looking equation in the combined gas law. So here's how this works. Okay, the key is, what are we assuming is constant? Okay, it says show that the combined gas law can be derived from the ideal gas law if you assume that the number of particles remains constant. Okay, so think about that for a second. Looking at our equation, which of these variables has to do with the number of particles of the ideal gas? Okay, well, that would be n, the number of moles. Remember, mole is an amount number. Okay, so n represents the number of moles of the ideal gas, which has to do with how many gas particles we actually have. So in this problem, we're basically assuming that n is constant. Okay, so watch what I can do here. If n is a constant, that basically means PV over RT is equal to a constant. Okay, that is a fixed value. If n is constant, then and it's an ideal gas, then PV over RT has to be a constant for any value of pressure, volume, and temperature. Okay, and so if we go from one pressure, volume, and temperature to 3 different pressure, volume, and temperature values. In other words, if we start at pressure 1, volume 1, and temperature 1, and we change the pressure, volume, and temperature, it doesn't matter what we change them to, they still have to be in this correct proportion. In other words, if we divide PV over RT, they still have to equal that constant because the number of particles, N, okay, the number of moles of the ideal gas has to remain constant. Okay, and so this has to be true for any values of pressure, volume, and temperature. And of course, since R is just a constant, if there's an R on both sides of the equation, that can cancel out. Okay, and so we have derived this, what we call the combined gas law. Okay, so P1 V1 over T1 equals P2 V2 over T2 from the ideal gas law. Okay, just by treating n as a constant and solving for it in the equation. Okay, and we could do something very similar to this to derive, Boyle's law or Charles' law or something like that if we wanted to, just by treating certain things as constant. If you go back in the notes and look at, for example, Boyle's law, I believe it says, to treat the amount constant and then one other thing constant. And so in those 3 gas laws we talked about at the beginning, you're treating 2 of these things as variables and 2 of them are as constants. And so through a very similar process, you can derive those other 3 gas laws starting from the ideal gas law. Okay, so pause there if you need to look at that. We're just going to do one more quick example. Example 2.5. Okay, it says a fixed mass of an ideal gas has a volume of 0.14 cubic meters at 301 Kelvin. Okay, so this is our temperature. If the temperature is increased to 365 Kelvin, so we have 2 temperatures. That's interesting. I'm going to label this temperature 1, and I'm going to label this temperature 2. Okay, that's very interesting. At the same pressure, what is its new volume? Okay, so this is still from the ideal gas law, but it's kind of similar to the problem we did a second ago, where now they're saying, okay, this is fixed and this is fixed. How are these other things changing? Okay, so they give me 2 temperatures actually, right? And they give me volume. I'm going to call this V1 for volume 1. That's the volume at the beginning, and they want the new volume V2. Okay, fixed mass means N is constant. Okay, because that means we have a constant number of gas particles. It also says the same pressure, so that means P is also constant. So if we start the ideal gas law, PV equals nRT, we basically have as a constant, we have the pressure and we have N. Okay, so if I get all of that on one side, if P over N is equal to, let's see, what would that be? RT over V. If this side is a constant, then the right side of the equation also has to be a constant. Okay, in other words, for any value of temperature and volume, this relationship has to be true. Okay, so RT1 over V1 has to equal RT2 over V2 for any value of temperature and volume, because remember, if the left side is constant, the right side has to be constant as well because there's an equal sign here. Okay, of course, R cancels because it's just the gas constant. And so here, we get one of those gas laws we talked about before. And from this point on, it's very easy to solve this problem because we have T1, it's 301. We have V1, that's 0.14. We have T2, it's 365. And so we can easily solve for V2 just using some basic math. And so I'm just going to write down the answer here. I'm just going to type that into my calculator after I rearrange this. And so that's how you would kind of derive the other gas laws from this one. So we get a volume of 0.17, so 7 cubic meters, okay, as our new volume. So in other words, the temperature has increased. That means the volume has also increased, and we talked about that before when we talked about the gas laws. Okay, so those are just some of the more basic examples doing calculations and doing concept questions with the ideal gas law. In the next video, it's going to be the last video, we're going to do a few more IB questions with the ideal gas law, and then we're going to wrap up this unit. We only have 1 or 2 more slides of notes over new material, and then we will be done with the material for this unit. And we'll probably have 1 more worksheet assignment over ideal gas law in the last little bit. Okay, so please let me know if you have any questions. I'll see you in the next video.